So tutorial number 10. We'll be talking about radiation. So I will start with a very brief explanation about radiation. Radiation is the rate at which energy is emitted by an object as a result of temperature increase or rise. All right. So basically, this is the definition of radiation. So the radiation wavelengths could be given. Radiation wavelengths. We call it lambda. Lambda is equal to C node over the frequency. All right. So C node is the speed of light, which is 3 multiplied by 10 to the power 8 meter per second. So this is the definition of the radiation wavelengths. So let's start. I'm gonna start this tutorial talking about the heat fluxes. If we have a flat plate that is exposed to incident heat radiation, we call it irradiation. So the heat fluxes. We're gonna start with the heat fluxes, and I will be doing energy balance to show you how many energy how many heats that are gonna be involved in this energy balance, and the types of different radiations. So if we draw a very simple schematic of a flat plate that is semi-transparent, plate, and this semi-transparent plate is exposed to an irradiation G. So G, we call it irradiation, or the incident radiation. All right. And so what happened to this incident radiation is either reflected and we give it the G reflected, or either absorbed, and we call it G absorbed, or transmitted. And we give it the name G trans. All right. So also there is another factor, which is emitted. E. We give it E. Right? So we have like five or four different energies here. So when we are doing energy balance on that flat surface, let's not include the the emissivity right now. I will include it later. So I don't want you be confused for now. So basically, G is equal to G. G is the incident one is equal to G reflected plus G absorbed plus G transmitted, which is G ref plus G abs plus G trans. If we divide this equation by total G, this is going to be G over G, which is going to be 1, G reflected over G incident plus G absorbed plus the total G, G transmitted plus the total G. So this is going to give you um, 1 is equal to rho reflectance, alpha absorptance, and tau transmittance. So rho is the reflectance. All of those are factors. Alpha is the absorptance, and tau is the transmittance. So this one is very, very, very important. And from here, we got this very important equation. So one is the summation of the reflectance, absorptance, and transmittance, which is telling you how much if we have a one incident radiation, how much is going to be reflected, how much is going to be absorbed, and how much is going to be transmitted. So transmittance is basically going through the the flat plate. All right, so let me write it here for you. So transmittance or transmission, tau is the fraction of heat that is transmitted, and absorptance or absorption, alpha, is the fraction of heat that is absorbed, and reflection, rho, is the fraction of heat that is reflected. All right. So this is the summation of the heat fluxes over a flat plate exposed to irradiation. And so another flat plate surface. So I'm going to talk about the different like another case, like if we have irradiation coming in. So we said that some is going to be transmitted and others going to be either absorbed or reflected. So we call something called radiosity. So radiosity is basically any kind of energy that leaving the surface. So we have different kind of energy leaving. Radiosity we call it J, all right, and irradiation, as I told you, is G. Transmitted is G, or this way, G transmission, right? So radiosity is any heat flux or heat leaving the surface. So radiosity we call it J, right? So J here is going to be E, emittance. So let's say that this is E, and another thing here G, reflected. So all of those are radiosity. So J is um, the emissivity or emittance plus G reflected plus G transmitted. All right, so this is the general equation of radiosity, which is the summation of heat flux leaving any kind of surface. And I just wanted to simplify this for you because we may be use it later in one problem. So J, so the emittance is basically the radiation emittance, which is epsilon sigma multiplied by the surface temperature to the power 4, which is depends on the surface temperature, plus G of the reflected heat flux. So we can substitute it by alpha, sorry, rho. This is rho multiplied by G, and the transmittance is going to be tau multiplied by G. Because as I told you before that rho is G reflected over G over total G, and tau is G transmitted over the total G. Right, guys, if you have any questions, just let me know. Like stop me I'm not seeing maybe I'm not seeing any comments because I'm writing on the tablet, so you can turn on your mic and stop and ask me any question, right?
I'm sorry.
Yes.
The radiosity equation, the first one. What is E?
Where is?
E. Where you have J is equal to E, the first one.
Yeah, E is the emittance of the surface. Emittance is I'm gonna come to you to it later, but emittance is the amount of energy that the surface emits as compared to a black body. All right, so it's a ratio between the how the surface is going to emit some amount of energy as compared to the black body, which is the perfect emitter. All right,
Okay,
so
thank you.
you're welcome. So this is gonna be J, and J is equal to epsilon sigma T surface to the power, which is depending on the surface temperature, right? All the other heat fluxes are depending on the material itself, the material of the surface, like alpha, rho, and transmittance. All of them are depending on the material of the surface. Surface material. while the emittance is depending on the surface temperature and the emissivity of the surface, right? So let's write it this way. I just want to do it on a general form, right? Yes, plus we can take G as rho plus tau, right? So do you remember when I told you one is equal to, this is one equation, and one is equal to rho plus tau plus alpha, then rho plus tau is going to be 1 minus alpha. So if the absorbance of any surface given to you, this is equation number 2. So this is the general equation. Epsilon sigma Ts to the power 4 plus G1 minus alpha, right? Special case here. Special case here. If the surface was opaque surface, like there is nothing to transmit it through. So the tau here is going to be 0. All right. So tau is going to be here 0. All right. So it's going to be the same case, exactly the same case. All right. So we no, it's not like this. This is gonna be, we can write it from the beginning. Like we can write the equation from the beginning. So again, we have to start from here again. All right. So J is equal to E plus G reflectance plus G transmittance, as long as E plus rho multiplied by G plus tau multiplied by G, as long as tau is 0. So this term is going to be cancelled out, and there is no transmittance at all at this problem, and J is going to be E plus rho multiplied by G, right? And so we are going to use this. Okay, we are going to use this one if this special case is achieved, right? So which is basically related to that one, right? 1 minus alpha is basically rho if tau is equal to 0, right? And also, I just wanted to define another thing, which is the radiation flux. So the radiation flux U double dash radiation is the amount of heat leaving the surface minus the amount of heat incident or incoming to the surface, or it is the difference between the outgoing and incoming radiation. J is the radiosity, as I told you, which is the outgoing radiation. G is the incoming radiation, which is irradiation or irradiance. So basically, it is when we apply this for, let's say that this is general plate, and that one was opaque surface. So the radiation is going to be different. So in case of the opaque surface, let's substitute this here. So Q double dash radiation is going to be E plus rho G minus G. So this is going to be E plus rho minus 1 multiplied by G, or this is going to be, as I told you, for on a bug surface, rho plus alpha plus tau is equal to 1 and tau is 0, so rho plus alpha is equal to 1, and rho minus 1 is going to be minus alpha. So if we substitute that here, it is going to be E minus alpha G, or epsilon sigma Ts to the power 4 minus alpha G. So epsilon emissivity, sigma surface emissivity. Sigma is the Stephen-Boltzmann constant. Stephen-Boltzmann constant, which is 5.67 multiplied by 10 to the power 8 watt per meter square Kelvin to the power 5, right? I just applied the radiation flux in case of big surface, because later I will be doing it for a general surface in problem number 4, problem number 3 specifically. So when I come to problem number 3, I will do it again for the general case. So take care when you have a special case like an opaque surface, or he might tell you that the upper surface is receiving some irradiation, but the lower surface is isolated. When the problem says that the lower surface is isolated, it means that there is no transmittance through the surface. So when there is no transmittance, so this is going to be obviously an opaque surface. All right. So any questions so far up till now? All right. So I will be talking about very quickly about the black body. Very quickly about the black body, and then I'm gonna solve 2 problems. So for black body, is basically a perfect emitter and a perfect absorber. So one moment, guys. Just give me one moment. All right. I'm sorry, guys. So a moment again. I'm sorry about that. So weird. Okay. So there's some problem with the recording and stuff. So again, perfect emitter and perfect absorber, and the emissivity of any black body is going to be sigma multiplied by t to the power 4. And the intensity, so this is the emissivity, and this is the intensity. I is going to be EP over pi, all right? And also lambda maximum multiplied by the temperature is going to be 2898. So this is basically if you want to find for any black body, if you want to find the maximum wavelength, at a specific temperature, so you got to be using this equation, right? And just read about the black body in the lecture, because from the lecture, because it's really very important. What is this? Okay. All right. So so let's solve some problem right now. I'm gonna solve the second problem, I think, or the first one. Yeah, it was the first one. So does anyone have any questions so far up to now? So far so good. All right. So question number one. Question number one is there is horizontal. Oh my God. Horizontal semi-transparent plate, and so let's draw the plate here, which is a semi-transparent plate. And that plate has an absorptivity of 0.4, right? So and there is some air flowing over that flat plate with a temperature T infinity of 310 K, and the heat transfer coefficient over this flat plate is going to be 50 watt per meter square Kelvin. And right, so given to you is J, which is the radiosity of 5500 watt per meter square. So this 55 basically is the flux, the radiosity flux. So we give it double dash here because it's what? Per meter square. So we give it double dash. It's also given to you. And given to you the surface temperature. Is 360 Kelvin. So he is asking for plate irradiation G, and he's asking for the emissivity epsilon. All right, so what we're gonna do is just draw a very simple schematic of that plate showing the irradiation coming in, right? And also there is Q double dash by convection going out because there is a flow of air going flowing over that flat plate with a heat transfer coefficient of 50. So there would be um, convection, and also going out here is J, which is given here. Right, so J is the radiosity going out of the surface, G is the irradiation coming into the surface, and Q convection because of the airflow over the plate. So what we're going to do is just do an energy balance. So if we do an energy balance, this is going to be energy in is equal to energy out. And the energy in that case here is going to be G, and energy out is going to be convection and radiosity. So there's going to be G, and energy out is going to be Q convection plus the J. And this should be multiplied by 2 because of the upper surface and the lower surface. As long as 2 is going to be multiplied by all of the terms, so we can cancel it immediately. But you maybe wanted to draw all of the heat fluxes coming in and coming out. And there is Q double dash convection from the other side, and there is J from this side as well. So that's like we're supposed to have 2G and 2 convection and 2 um, radiosity, but we cancel all of them, or we can write it in one surface and multiply it by 2, but it doesn't matter. All right, so we want that one because the problem is asking for that one. G is going to be Q double dash convection, which is H multiplied by delta T plus plus J double dash. All right, and so here G is equal to H multiplied by T surface minus T infinity plus J double dash. H was 50. All here is given to you. Surface temperature was 360 Kelvin minus the ambient temperature 25, or no, it was 310 Kelvin plus 5500. So we got G as 8000 watt per meter square. So this is the total amount of incident radiation. All right, and the problem is also asked for and emissivity. So from where we're going to get the emissivity? So we've got the emissivity from here. Do we remember that J is basically E plus G reflectance plus G transmittance, and this J is equal to E plus rho multiplied by G plus tau multiplied by G. J is also equal to E plus rho plus tau multiplied by G. And what is given to you here? Given is alpha equal to 0.4. So when you write this rho plus tau plus alpha is 0.4, then rho plus tau, sorry, that is equal to 1, is equal to 1 minus alpha. So we take this and substitute it here. So J is equal to E plus 1 minus alpha multiplied by G. So we have G, we have alpha, we have G. We just left with E that has the emissivity. So J basically is going to be epsilon sigma T surface to the power 4 plus 1 minus alpha multiplied by G. And J is 5500 as given to you, is equal to the emissivity, which is the thing that we want. Sigma is 5.767 multiplied 10 to the negative 8. Surface temperature is 360 to the power 4 plus 1 minus alpha, which is given to you is 0.4 multiplied by G that we just got right now is 8,000. From here, you're going to get epsilon of 0.74. So those are the two requirements. Does anyone have any questions so far up to now? Any questions?
Pretty straightforward.
Huh?
No, it's pretty straightforward.
All right, very good. So I just want you guys ask the prof about something because it seems not clear for me. So these temperatures. So please ask the prof. Prof, the solution manual is giving two things. Sometimes he do it this way, Ts to the power 4, and sometimes he do it this way, Ts to the power 4 minus T reference to the power 4, or T surrounding. Not the reference, is the surrounding. So please ask the prof about which one, because the solution manual is giving both, all right? So I just want you ask the prof about this, which one is more correct for you, so you don't have to worry in the exam, right? So question number 3, which is the last question, I try to do it in that last 10 minutes. Question number 3 is basically when we have a solar flux. So solar flux is basically the incident radiation, which is G is given at 1000 watt per meter square, which is a flux as well. Solar flux incident. And is giving to you a flat plate. And he told you that this plate is isolated from one side, from the bottom side. When it says it's isolated, so tau basically is equal to 0. Tau is the transmittance, and giving to you alpha 0.9, and the emittance is 0.2. So when we draw, tau is 0 because because of the bottom surface. Is insulated. So tau is equal to 0. And when we draw the fluxes, so basically we have G and Q double dash. Also we have convection because he said that there is a stream of air flowing over this flat plate at a temperature of 25 degrees Celsius and heat transfer coefficient of 20 watt per meter square Kelvin. So basically we have also convection here and we have J. So basically if you wanna, what he is asking for is asking for the convection heat flux. And radiation heat flux. And the surface temperature. What is the surface temperature? The surface temperature is not given to you here, which is not that bad. We can get it from the energy balance. So let's start with, usually when you have something, when you have a problem like that, you usually start with energy balance. Which is going to be similar to the previous problem, Q double dash convection plus G. All right, so the only thing that we have here is G. G is equal to Q double dash convection, which is H multiplied by T surface minus T infinity. We don't know the surface temperature. Actually, we are asking for it. We have G, we have H, we have T infinity plus J. So this J, let's say this J is for an opaque surface, and J for opaque surface is E plus G reflectance plus G transmittance. But for an opaque surface, transmittance is 0. So J is E plus J reflectance. So J is E plus rho multiplied by G, which is given to you. So let's substitute this here in that equation. So G is equal to H Ts minus T infinity plus E plus rho G. Let's get this rho G and get it to the other side here. So basically we will be left with G is a common factor, 1 minus rho H Ts minus T infinity plus E. All right. So we know that 1 plus, we know that alpha plus tau plus rho is equal to 1. This is 0. Alpha is 0.9, then rho is equal to 0.1. So now we have rho. We have G, we have rho, we have H, Ts, we don't know this one, T infinity, we know T infinity. And so this one is going to be epsilon sigma T surface to the power 4. So we're gonna left with an equation that has only T surface as an unknown. So G was 1000, 1 minus 0.1 is equal to H, the heat transfer coefficient was 20, and that's Ts minus T infinity, let's write it in Kelvin. So we will be, so the only unknown is going to be getting in Kelvin because we have stability here in Kelvin. So the emissivity is given to you was 0.2 or 0.2. Sigma is 5.67 multiplied by 10 to the negative 8, and T surface to the power 4. So from here, if you solve that problem in your calculator, you're gonna get, we get the surface temperature. It was 339.4 Kelvin. And this is one of the requirements. And the first requirement was Q double dash convection is H multiplied by Ts minus T infinity. H was 20, T surface, we just get it, and T infinity 280, 298. So this is going to give you Q double dash convection of 838 watt per meter square. The second problem. And from the definition of Q double dash radiation is the difference between the heat flux leaving the surface minus G, and after doing the whole thing, the derivation, we are going to be left with, or we can do it here right now. So J for opaque surface is E plus rho G minus G, which is E plus rho minus 1 multiplied by G, or E minus alpha G. So E is the emissivity, sigma, T surface to the power 4 minus alpha, which is 0.9 multiplied by 1000. This is given to you, right? Sorry, let's write it this way. Alpha G, and here I'm going to substitute by numbers. That is 0.2, sigma is 5.67 multiplied by 10 to the negative 8. T surface was 339 to the power 4 minus alpha multiplied by 1000. So from here, you're going to get Q double dash radiation, which is basically the same as Q double dash convection, but you got to double check if both of them are the same. That was 838 watt per meter square. So double check that both are the same. So guys, thank you very much. I appreciate your attendance today. And I just wanted to remind you, please don't forget to submit your the course feedback and evaluation. I will be happy if some of you just leave the feedback, because I take it to improve myself a little bit. So if you have any recommendation to improve the tutorial so far, just leave a comment or because this evaluation is very important. So thank you very much. Does anyone have any questions so far?
Yeah, Sherry, for TS, I got a different value.
For the what?
TS, the surface temperature.
Surface temperature, what value did you get?
335. And then when I calculated the Q radiation, it's not the same value as the Q.
Okay.
fraction?
All right, just take the value that you've got. Just take the value that you've got. I didn't calculate it because you don't have a calculator to here, but I just write it from the solution manual. So I'm gonna upload.
So it means that your Q radiation will not be equal to your.
Yeah, yeah. It doesn't really like the sequence is really more important than the numbers. So the numbers doesn't have like very like we don't consider the number as is to be accurate or something like that, but the sequence of solution is really more important. And that's how I did with your project
Oh,
because I think none of you guys have I don't know about Dr. Siemens section, but none of you guys have got the correct final answer. So I've considered all the marks on the project procedure and how you analyze the problem. So that's more important than the values.
okay, cool. Thanks, Sherry.
Good. Yeah, you're welcome. So any one of you guys have any question or any problem? Please again, don't forget to submit the course feedback and evaluation. Is really, really important. And just say the truth. And if you have any recommendation, I'm very open to any recommendation or any suggestion. And yeah, thank you very much. And I'll see you next time. Thank you, guys.